email address. So the housekeeping, this, I would like to emphasize that the summary lectures are supplementary. You have to watch the main lectures, right? So please don't just watch this one and then think everything is done. That's not the case. You have to watch the main lecture, and then this is supplementary. So you may actually, watch the recorded ones right at the end of the course before your exams, to prepare for your exam, the final exam, right? So the lecture will be delivered online from 5:30 to 7 on Tuesday, and it will be on MS Teams. This chat room is available to you in MS Teams throughout the week. So if you do have questions that suddenly pops up in your head during the week, you can actually write the questions down there, and then when I see it, I will try to address it. Or if your classmates see it, and then if they can answer it, they can also contribute to the discussion, right? If you have any feedback, like you can't hear my audio or you don't understand what I'm saying, please do give me feedback to my email address. If you have also questions, you can email me too. Right, so part 2. So part 1 was on optics. So you did geometrical optics, where you had the refraction of light, image forming, and that sort of stuff. And also there were physical optics or wave nature of optics, we call it, where you did the interference, fringes, and diffraction, things like that. So these 4 weeks, the first 4 weeks, covered the optics part of the physics foundation for EEE. The second part is going to be on electromagnetism, which is a study of physical interaction between electrically charged particles. And this, in fact, is probably the most important physics in EEE, because it forms the entire basis of the EEE technology, like electronics and communications and computers and everything, right? So electromagnetic phenomena is a natural phenomena. So you can actually see this kind of lightning, and that in fact is a naturally occurring electromagnetic phenomena. And it happens because the entire universe, the particles that makes up the entire universe, which we call atoms, they do have electrically charged particles that are interacting within the particle and between the particles. Okay, so and that essentially drives the entire electromagnetism that we see around. So these kind of microscopic interactions lead to this kind of macroscopic phenomena that we observe naturally. Also, we make good use of them. A lot of the technologies that you use, your mobile phone and your computer and everything, in fact, uses electromagnetism. This has a pretty old form, but communication, is based on electromagnetic wave propagation in the free space. This is wireless communication, or it could also be wired communication, like you plug your communication device through the wall socket, and then you can also so that technology is entirely based on electromagnetism, as well as your CPU, your computer, and your electronic, your fridge, your television, whatever that you have a lot of them in your house, I suppose. Okay. Right. So I just want to quickly talk about what sort of topics we're going to cover in this part 2 of the course. So in week 5, which is today, we'll be covering electric fields, and these are the corresponding chapters in your textbook, which is the survey. And then week 6 is going to be Gauss's law, and then week 7 we're going to cover actually 2 topics: electric potential and capacitance and dielectric. And then we will have recess after that. And then these 2 weeks are after the recess. And you will have your quiz 2. I understand your quiz 1 is this Saturday, what I read. And quiz 2 is going to be on these 3 weeks of content, which are four topics, right? So your quiz 2, which will happen, I think already the date is set, another Saturday sometime, will be on these 4. Okay, so these 2 are on magnetism and electromagnetism. So the first 3 weeks, or week 5 to week 7, are on electricity and electric charges and forces and electric fields, whereas the week 8 and 9, which are the last 2 weeks of the second part, are going to be on the electromagnetism, which looks at how the electric fields interact with the magnetic fields and so on. Okay, so that is going to be different part, but that is not going to be part of your quiz, just to fully understand what you have to study for quiz 2. Okay, of course, in the exam you will be tested on everything. So up to this point, any questions up to this point before we actually get into our topic today? If not, then I think, okay, go to electric fields. So electromagnetism is a study of how the electrically charged particles interact with each other. So what does it mean by electrically charged particles? There are actually 2 types of charges that you can find in this universe. First is positive charge, and second is negative charge. So when you have 2 objects that are charged with the same sign or same polarity, we call it, then they will repel each other. So you see these 2 positive charges, they will repel each other. And when you have the opposite, the objects of the opposite charges, then they will attract one another, right? So what about if you just have 1 charge? Does it do anything? So if you just have 1 charge, there's no attraction or repulsion. It just stays there. But there's only when you have the second charge, there will be interaction, depending on whether the second charge has the same sign as the first one, or it has the opposite charge as the first one. Okay. So electric force between the 2 charges are calculated using so-called the Coulomb's law. Okay, so this Fe is the electric force, and you can calculate the force acting on Q1 due to Q2 using this equation, which says Ke, which is a constant. It's a Coulomb's constant, and you multiply the charges, two charges together, and then you divide it by the square of the distance between the 2 charges. Okay, and then depending on whether Q1 and Q2 are same or different, the direction of the force will be determined. So if this force Fe is going to act on both particles, because on Q1 the effect of the Q2 will act on Q1, and then the force will be act on Q1 itself, and likewise the effect of Q1 will act on Q2, and then the same force will act on Q2. But you can kind of see that you have the same magnitude of the force, but the directions are opposite to each other. Okay. So Ke is a Coulomb's constant, which is given by like 8.99 times 10 to the power of 9, and then you have all these units, which in fact is also equal to 1/4 pi epsilon 0. And this epsilon 0 is so-called permittivity of free space, which is given by another number. Okay, and we will see at one point why we use this Coulomb's constant Ke, and then there's also another constant epsilon 0 when we get to, I think, next week's lecture. So forces, as you understand, they are vector quantity. So this equation only gives us the magnitude of the force, and r is just an absolute distance between the two particles. But because force is a vector quantity, that also means then we have to understand in which direction the force is going to act on. So this little arrow on top of F means it's a vector quantity. So it has direction and magnitude, right? And this direction is given by this unit vector. So this is just a representation. So if I have something with a hat on top of it, that means it's a unit vector. What is a unit vector? Unit vector only gives the direction. So the size of the unit vector is always 1. So what I'm doing here is I'm just multiplying 1 to whatever I have calculated here, which is not going to change the magnitude of it. But because r with the hat has a direction, it is going to give me some direction. And that's going to be the direction of my force. Okay, so that's what this equation means. Okay. So what F12 means is that the force acting on second particle, or Q2, due to the presence of Q1. So if we didn't have Q1, right? If we didn't have Q1, there would be no force acting on Q2. So the force would be 0, because if we didn't have Q1, that would be 0, and the entire thing would be 0, right? Whereas, so this notation means this is the force that is acting on Q2 due to the particle Q1. Okay, and that also means the direction that is pointing from Q1 towards Q2. Okay, this is a unit vector, which is this little black arrow that is pointing in the direction from Q1 to Q2. That's exactly what it means. And then you can see that the equal and opposite force is going to act on the other particle, as I said, from this diagram also. Okay, and we can also write that in this kind of vector representation. So this is going to be the negative direction of the force that is acting on the first particle due to the second charged particle. And then vice versa. Okay, so this is a diagram where you have two charges of the same sign. They will be repelling like that. And then this one is attracting. Now this direction of the force is in fact automatically taken care of by the multiplication here, because if the two Q's are of the same sign, you will always end up having positive here, right? So the force acting on would be in the same direction as the unit vector direction of the unit vector, right? Whereas in this case, when you have two charges of opposite signs, then the two multiplication of the two is going to be negative. That means the force will be acting in the opposite direction to the direction of the unit vector. Okay. All right. So let's take a look at an example. So it's a simple example. In the following diagram, this is 25 microcoulomb. These two are both 25 microcoulomb, and then we have one Q in the middle. And then this distance is 35 centimeters, and this distance is 70 centimeters. So what is the magnitude of the electrostatic force on Q? So if we want to calculate the force acting on Q, then, okay, first, what causes the force acting on Q? It's going to be the presence of this Q, okay? So we already have a Q, but then because there is another Q there, there's going to be a force acting on this one, right? And then there's another Q further out, this one. over 2d at a distance of 2d. And that's also going to cause some force here, right? So we can kind of see both Q and big Q and small q, they are positive. They are of the same sign. That means that force acting on this small q due to this big Q is going to be away from this big Q, right? So, and then same here, because this also the same charge, the force acting is going to be on this direction, away from this big Q. So what we can do is we can calculate each of these two forces separately acting on the small q, and then you can add them together, or you can basically do a vector sum, because we have calculated two vectors. First vector is this one, due to this red q, whereas the second vector of force vector is due to this green q, right? And because the vectors are acting in the opposite direction, you have to take the differences to get the magnitude of the net force. So net force is always the vector sum of all the forces acting on that particular element or particle or object. Okay, so in this case, I get 4.13 newtons. And because this one is closer, right? This red one is closer, so we have in the denominator we have d squared here, so that will give us a bigger magnitude f here, caused by this red q. So the net force is going to be acting in the positive x direction. So I suppose everything up to this point is very straightforward. Any questions? Okay, all right, then we've understood the Coulomb's force, okay? And that's actually the beginning of everything, okay? So the Coulomb's force, the force acting between the charges actually gives the electric field, and all the advanced notations and quantities, they are all derived from the fact that the two multiple, when you have two charges of the two objects of charge with electrically charged objects, they will have force between them. So that everything is derived from that. Okay. So we'll look at electric fields. So the definition of electric field is that you will have force, right? You will have force if you have two particles. But if you make the size of the second particle small and small, and then you divide it by the size of the particle, then you will eventually end up having the effect of only one particle. Okay. So what I mean by that is, for instance, in this, for instance, let's just talk about this case here, right? For instance, we have this big particle, and then when we only have this single particle, there's not going to be any force around it. So we will not know the presence of this particle if we don't have another particle, if you understand what I mean. The only way that we know that there is this charged particle is that by having another charged particle. If we don't have that, we don't have the second charged particle, then we don't know that there is this charged particle, because we wouldn't have any force, right? But as soon as we have another charged particle, then there will be a force, right? There will be a force, and we know how to calculate that force now. Okay, but we want to know the effect of having the influence this particle has on the surrounding. So if we want to know that, then what we can do is we can have a very small test particle, charged particle, which we call Q0, and then we just put it there, and then we know by putting it here, there's going to be a big force that way, and then if I put it here, it's going to be a big force that way. If I put it here, it's going to be a big force that way. So some sort of force is going to happen as soon as I put a very small particle here. Okay. Now, if I make this particle to be very close to zero, and then I divide it by Q0 such that the effect of this becomes negligible, then we have what so-called electric field. Okay, then electric field can be present without having the second particle. So with just one particle, we can still talk about electric field, because what that means is that, okay, when we just have one particle, of course, we don't know whether there is a particle or not unless we have the second test particle to know it. But what electric field tells us is that as soon as we have a particle, which way is the force going to be directed towards? And then also, how big is that force going to be? That's what electric field is telling us. And it is measured in newtons per coulomb. So that means if we, under the presence of this electric field, if we bring in a coulomb of charge, then we can calculate how much force it will act on that charge. Okay, so that's what the meaning of electric field is. And if you do a unit analysis on this, you will see that this also is equivalent to volts per meter. So these two are actually the same, exactly the same meaning. Okay. So because we are, in this case, the force is going to be Q times Q0, right? Q naught, Q times Q naught. But because for getting the electric field, we need to divide it by Q naught, and then we take the limit of Q naught going to 0, then we end up having this equation for the electric field. So the electric field can be present with just single particles like that. Okay. So with a positive Q, you know that the electric field is going to be directed away from the charge, because this test charge that we use is a small positive test charge here, right? Q naught is positive test charge. That means when we put a small positive test charge, the force is going to act in the direction of these arrows. So we can say that the electric field of a positively charged particle is going to be radially outwards from the charge. Okay, and with a negative charge, of course, when we have a small positive test charge, it's going to be attracted towards the negative charge. So we can say that the negative charge has electric fields that is coming in radially inward towards the negative charge itself. And then the magnitude of it, we derived it here, and then we can see that it decreases with r to the power of 2. So it is inversely proportional to the r squared. Right. So if you remember how we did the example for calculating the force acting on a particle due to multiple charges, we had to add the force vectors calculated from each of these different charged particles. And then we add them, and then we were calculating the net force. So similarly, we can calculate electric field due to multiple point charges in the same way. So how we calculate, for instance, in this example, how we calculate the electric field in the middle point here, somewhere in the middle, we call P. What we do is we need to calculate the electric field caused by Q1, the first particle. And then, oh, that's acting this way because it's positive, so it will be acting that way, away from the positive charge. And then we calculate the electric field at the same point due to the second charge, this. And then E3 is going to be towards the third particle, because now here in this example, the third particle is negative. You do a vector sum of the three, and then you will get the electric field at that point. And by doing the same thing, you can actually map out how the electric field is going to behave in this space around these particles. Okay? And that's called electric field lines, which we're going to talk about later on. Okay? So mathematically expressing this, we have the electric field this is the electric field vector. The net electric field that is acting on P is going to be the electric field due to the first particle, due to the second particle. That should be Q2, Q3, and 2, 3. I'm sorry. Okay. So these should you need to add up all the electric field caused by each of these particles, and then do a vector sum. So these are unit vectors. Of course, they indicate which direction the field is acting on, and then finally you can also calculate the direction also of the net electric field. So that's how you can calculate in 3 steps. You calculate each of these electric fields at P, and then you can decompose it. So in this case, I will decompose it to X and Y components, because in this example, I'm not taking any Z components. Z is going to be coming in and out of the slide, but I don't have that. So this is going to be the X component of it, Y component of it. This one also, I have Y component and X component. And this one seems like I don't have any Y component, I just have X component. And I can actually add all the X components together and then add all the Y components together. Of course, keeping in mind the direction. So if it was negative, then I should subtract it. If it was positive, I should keep on adding them. And then eventually I will have the electric fields in the net electric field in the X direction and net electric field in the Y direction, which will fully characterize the electric field of the net electric field at point P. Okay, so let's take a look at this example. So this example is taken from one of the past year exam questions. So you can expect a similar type of questions in your exams. So we have 4 point charges, Q1, 5 microcoulomb, Q2, -7, Q3, and Q4, okay? And these are at the 4 corners of a rectangle, and the dimensions of the rectangle is given here. And we need to determine the electric field at point A, which is the midpoint in the rectangle. So how would you do that? How would you do that? I would do it by calculating the electric field caused by Q1 first on this one, and then calculate that vector, and then calculate the electric field caused by Q2 at this point, calculate that vector, calculate this one, that one, and then add all the vectors together. Okay. So doing that, E1, because E1 is positive, it's going to be directed this way, right? And then how do we calculate? So in order to calculate the magnitude of E1, we need to know the magnitude of Q1, which is already given, 5 microcoulomb. And then we also need to know the distance, which is from here to here. How do we get that distance? Which I'm going to call it X. We can get it by using Pythagoras, right? Because this is a right angle triangle where this length is half of 3 centimeters, and that length is half of 4, which is 2 centimeters. So it's 2, 3, and then that one you can calculate. So you can calculate that using the Pythagoras. And when we do that, we get a number. So that is going to be the size of this arrow or this vector. Okay, that's going to be the size of that vector. And now we need to, because we're going to be, we will be adding whole lot of we're going to be adding a whole lot of 2-dimensional vectors like like in the XY plane. It is a good idea to decompose this into 2 orthogonal vectors, meaning we want to have X component and Y component. So in order to get the X component, if this is theta, then that angle is going to be theta as well. So in order to get the X component, we can do cosine theta. Okay. And then also in order to get the Y component, we can do sine theta, right? But we have to make sure we are using the right sign because E1 is directed that way, so it's moving in the positive direction in the X, whereas in the Y direction it's moving down, meaning it's going in the negative direction. So I put a negative sign there. Okay. So when I do this computation with the theta, which theta is calculated here, 2, 3. So this comes from this also comes from the tangent, arc tangent, because I have a right angle triangle here with this 2 and this 3. So in order to calculate this theta or that theta, which is the same, I can take the inverse of the tangent of 2/3, then which is going to be some angle. And then I can substitute those values in, and then I can get the X component and Y component. So I hope you understand these notations. I with a hat means it's a unit vector. It's a very common notation for a unit vector in the X, positive X direction. Okay. Whereas J means a unit vector, positive unit vector in the positive Y direction in the 3-dimensional space. Okay. And of course, if we have a third dimension, which is Z, the positive Z is often annotated with the K unit vector. So it's IJK. Right? So in this case, we have positive X direction. This E1 is directed in the positive X direction, whereas the E1 is directed in the negative Y direction because we have minus here. Okay. And that the magnitude of, remember the magnitude of these unit vectors are 1, so it doesn't change the value itself, just gives the direction. And so that's going to be E1. Same way we can calculate E2. E2, we know this is positive, so E2 is also going to be pointing away from, we're looking at Q2. Okay, Q2 is negative, so Q2 is going to cause the direction of E2 is going to be towards Q2, right? At this point, because it is negative. So knowing that, we actually can use exactly the same X because the distance doesn't change. X is the same. And then angle also the same. Angle doesn't change. But in this case, we have E2 is in the positive X direction and also positive Y direction because it's moving that way. So we can get that. We can do same for E3, which is caused by the Q3, and it's away from Q3. And then we apply the same logic. And E4 is going to be due to this one. And again, this is positive, so the direction of the electric field is going to be that way. And then we apply the same thing, and then we end up having all E1, E2, E3, E4 all decomposed into X and Y components, as you can see here. Then we can do the vector sum. So when you do the vector sum, all the X components can be added together because they are actually on a same line or single line. And all the Y components can also be added together because they're all on the same Y line. And we can get eventually we can get the net electric field at point A, which is this. So it says the net electric field is pointing in which direction? Actually, positive X and positive Y. So some that way. So, any questions up to this point on electric field and adding all the electric fields together? Okay, seems no questions. Then we will take a look at electric fields of continuous charge distribution. So we've been looking at, until this point, we've been looking at electric fields due to point charges. So we assume that the charge is at a single point somewhere in space, right? So what we had to do was we caused by this one, we add them together, we add here. But in reality, the charges are distributed over some volume or space distributed over some volume in the space. Okay, so in which case, then how do you deal with it? So how do you, because now we are not dealing with point charges, we have to deal with some charge distribution over some volume in space. So how we do it is actually similar to what we did with the point charges. So what we did with the point charges is that we calculated the contribution of each point charges, and then we added them all together. We added all the vectors together, right? This is how we did it with this the rectangle and everything. This one, instead of, because we don't have point charges, what we have to now do is we need to divide the charge distribution into a very, very small element. And then we have to calculate the effect caused by each of these small elements, and then we have to add them all together. Okay. So let's take a look at this example. So this bluish shape is kind of a charge distribution that we have in the space. Okay. So what we need to do is we need to divide them into very small pieces, like these little yellow boxes. And then from each of these boxes, we need to calculate the contribution of each of these boxes at the point P. You know, in order to calculate the electric field at point P, we need to calculate the contributions from all of these each small elements. And then we need to do a vector sum of them. Now, if we do all these, if we divide the entire continuous charge distribution into these small elements, and then we add them all together, then we will eventually get the electric field at this point due to the entire system, right? So that's what we're going to do. And of course, we have to, in order to be able to do that, we need to make sure these elements are small enough, because if it's too big, it's going to, if it's big, it's going to occupy certain space, and you will not be able to represent an arbitrary, continuous charge distribution of arbitrary shape. Okay. So that actually leads us to taking the limit of this Qi going to 0, and that's going to give us this integration. Okay, so coming back to what we have to do in steps. First, we divide the charge distribution into infinitely small elements, like what we have done here, and then we compute each contribution from each of these elements, and then we add them all together. But when we add them all together, we make sure that when we do this calculation, we make sure that each of these little elements are small enough, meaning we make them go to limit of 0. Of course, you can't make them 0, but it will go very close to 0, and that will be equivalent to doing an integration over the entire charge distribution. So here I've been talking about charge distribution over some volume. I think, okay, I've drawn, I can't draw a volume on two-dimensional slide, but you can assume that this is a volume. But of course, we can also do it over line. Like in this case, we will need line charge density. So if we assume that the charge is distributed uniformly, if the charge Q is a charge, is distributed uniformly along the length of the line, then we can calculate the line charge density lambda, which is going to be coulombs per meter, because charge is measured in coulombs. So per meter unit length of the continuous charge distribution over line, how much charge is contained within per unit meter. Okay, and in order to calculate that little dq small element within this length distribution, you can multiply the charge distribution by the small length element dl. If it was surface, it's going to be, we often use the symbol sigma. And this is going to be the surface charge density, which is going to be the coulomb over meter squared per unit area. Okay, so if you want to calculate how much charge in that small element for a surface charge distribution, then you need to multiply the sigma by dA. Then the area unit is going to be meter squared. So you cancel that, and then you just end up having C, which is going to be the unit for the charge, or the charge contained within that small element of area. Okay, and volume is the same, but in this case we often use the notation rho to denote the volume charge density, and that's going to be the total charge divided by the volume if we assume that the charge density is uniform across the entire volume, and the unit of that is going to be coulombs per meter cube. And in order to calculate, of course, the small element, the charge contained within the small element d v, then you multiply dv by rho, okay, and then you get that dq. So I hope the whole concept is clear. These concepts going to be used quite regularly when you are solving the problems in this part. Right. So we'll take another look at an example. So we have a uniformly charged rod of length 14 centimeters. So this is a rod of 14 centimeters, but it is bent into a shape of a semicircle. So we have a semicircle. If the rod has a total charge of minus 7.5 microcoulomb, find the magnitude and direction of the electric field at O, the center of the semicircle. So this is going to be the center of, it's actually the center of the circle, and it's not actually center of the semicircle, maybe, or is it defined like that? Okay. Anyway, so how are we going to do that? So what we need to do is, because this is a line charge distribution, right? It's a line charge distribution. We have to calculate the lambda. Lambda is because it is uniformly distributed. The charge is uniformly distributed. It's not that difficult to calculate lambda, which is going to be minus 7.5 microcoulomb divided by the length of the bent section, which is actually going to be 14 centimeters. Okay, so or if you know what the radius of this system is, it's going to be pi r, because pi r is going to give you it's going to give you the circumference, is the arc length of a semicircle. And then we need to, so this is a diagram how to calculate the small contribution dq to calculate the small electric field caused by a small charge element dq on the road. Okay. So in order to calculate dE caused by this small section dl, then this is going to be the equation, because the distance between dl, this part, and then that center of the circle is always going to be r. So we can put r squared there. And then dq, in fact, is going to be the charge, a small element of charge contained within this very little length dl. So in order to calculate dq, remember, for line charge distribution, it's going to be lambda times dl. And we know that lambda is going to be q over pi r in this case, or you can actually use the number directly, minus 7.5 microcoulomb divided by 14 centimeters, because this is the length of the rod which was bent. So the entire length itself is actually 14 centimeters. And then that is going to give us, substituting this in here, and then also, substituting that in, then we're going to get this q pi r, and then dl. How do we get dl? dl is this little arc length, right? arc length that is caused by a very little angle, d theta. So in order to get that dl, we need to multiply d theta by the radius to get the arc length, because arc length is the angle in radian times the radius. Okay, so we can multiply those two together to get the little length there, and then that actually gives us dl. So we can get lambda times dl expressed in this way. Okay, and then if you cancel a few things out, then we get theta pi over d theta. Now the entire thing is expressed in with the angle. Instead of dl, we are using now angle. Now this makes a lot of things easier because we know we have a semicircle, so when we do the integration, we can use the angle theta, because with the semicircle, it will be from, let's say, from angle 0 to angle pi. So we can take an integration over that that limits, those two limits. Okay. So when we substitute that dq into this equation, we substitute this one into there, then we end up having that, and this is for dE, right? And then this dE, we have two components. We have dE x component and dE y component. What do you think is going to happen to dy component? Dy component is actually going to be cancelled out if you add them all together. Okay, EY component is going to get cancelled out if you add them all the DEY component together, because of the symmetry. Because when you are calculating this part here, your DEY is going to be that direction. When you're calculating that part there, it's going to be towards that direction, and then they will have the same magnitude. So these two will cancel. And then same, when you're calculating here, DEY is going to be that way. No. That again, it's going to be that way, but it's going to have the same magnitude as the one calculated over here, because the charge stored across this bent road is going to be equal, and then the distance is always the equal. So then the y components all get cancelled out, and then only the x components survive, right? But you can also look at that. You can also prove that mathematically. Because when we take the, in order to get the x component, when this is theta, we know that is going to be theta, because that's theta and that's going to be theta there due to the opposite angle. And then that means dEy is going to be the cosine theta of the dE, which is this one. And then dEx is going to be the sine theta. That one is going to be the sine theta of dE, which is that one. Okay. And then when you do the integration, you need to do the integration over 0 to pi, because this theta is going to vary. So when you do this little calculation starting from here and then you're ending there, it will start, your theta is going to start from 0 and it will end when theta becomes pi. Okay. So you can do this integration, and then you end up having a finite value for the x component of E. Whereas when you do the integration over the y, you will have 0. You end up having 0 in the end. Okay. So then you can say that the net electric field acting at the point O is just going to have one component, which is x component, like that. Is that any questions on this? Okay. So why do we have negative value here? Why do we have negative value here? That's because the entire rod is charged of negative charges, right? So it has net negative charge here. So eventually, the electric field is going to be acting towards the rod from the center of the semicircle, from the point O. Right. So that is for calculating the electric fields of continuous charge distribution. We will go to the next topic, which is on the electric field lines. So when you have a charge, you can calculate electric field around the charge, right? And you can also calculate electric fields around many charges, or also continuous distribution of charges. You can calculate electric field around them. Okay, so drawing electric field line is a very useful way to visualize, how the electric field is acting in the space, and it carries in which direction the electric field is acting, as well as how strong the electric field is. Okay, so these are just some examples of the electric field lines drawn. So these are just two charged plates of opposite charges. Then you can see that around the middle of the two plates, the electric fields are going in straight lines, whereas along the sides, they are sort of, at an angle or going at some radius. And then these are some system of charges that are placed at equal distances away from each other. And then you can kind of see how the electric field lines are going when you have this kind of system of charges. Okay. That's just some example there. So there are a few rules about electric field lines. So electric field lines, when you draw the electric field lines, you have to draw the direction, right? So when you draw the direction, the lines always start from positive charge, and then they end the negative charge. So it shows what does it show? It shows when your positive test charge is placed, in which direction that positive test charge will move. This is exactly what it is showing, right? So the electric field, direction of the electric field at a specific point on the electric field line is going to be tangential to the electric field line itself. Okay, so if I have drawn an electric field line of that, and then I want to find out in which direction is the electric field at that point there, then I just draw a tangential line on that point, and then that's going to be the direction of my electric field. So in this case, we can calculate that, we can understand that the electric field is going to be pointing this way at that point. It's going to be pointing this way at that point and pointing that way at that point there. Okay, and field lines always begin on the positive charge, so we call it source. Source means something is coming up, right? And then it ends always on a negative charge, so we call it sink. So if we don't have positive charge, or if we don't have negative charge, the lines cannot be generated without having positive charge, and the lines cannot be destroyed or terminated without having a negative charge. So they will always start from a positive charge, and it has to end at negative charges. Okay. All these diagrams, when we actually end here, it doesn't mean there is a negative charge. It's just going to go infinitely large and then perhaps come back here, right? Or it should be this way, of course, looking at the direction. Same with this, same with that. It's just going to be a very long loop, but because we have a limited space on the slide, I have to terminate the lines, but it doesn't mean that there are negative charges here. It just means that I have, cropped the picture out. And same here, of course. Okay. The number of lines, also the number of lines leaving or approaching a charge is proportional to the magnitude of the charge. So in this case, how many lines is leaving this charge? Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 lines are leaving. And then I think if I count, I probably have 15 lines approaching the negative charge. That means these are of the same magnitude. The charges are of the same magnitude, but opposite sign, right? So if this was 2 times larger, then there should be 2 times more lines leaving when you draw it, okay? 2 times more lines leaving the source or positive charge, and then those lines approaching the negative charge. So that's what it means by the charge is proportional to the magnitude. The number of lines is proportional to the magnitude of the charge. Okay. Now, when you draw them, you never ever cross the 2 field lines in a single point. Okay. That's because when a test particle is placed here, it has to move only in one direction. It cannot. So because if you have a crossing point like that, then I put a test positive charge here. Then if I have two field lines crossing, then I wouldn't know in which direction the positive charge should move, right? So you can never actually have field lines that are crossing each other. What you have to do is you always have to do a vector sum. If this positive charge is producing an electric field that way, and then if this positive charge is producing an electric field that way, then at this point, rather than crossing them, what you have to do is you have to calculate the vector sum of the two and then draw the line that way. So if you have two positive charges spaced closely together, then you can see that in the middle here, instead of crossing like that, you have a field going upwards like that. So for the previous question, Matt has a question on the chat box. For the previous question regarding the half rod, must DL be a small point of the whole rod? Also, can you elaborate on Rx theta? Okay, I will come back to this. After I finish the electric field lines. Okay, is that okay, Matt? Because I think I just have like 2 more slides and then I'm finished. Okay, for the lecture part. Okay, I will come back to it definitely. Okay, so that is going to be the field lines never crossing. So you can see that the field lines never cross here. And then the density of the field lines passing through a surface represents the magnitude of the field. Okay, so if your electric field, so you have to imagine these field lines are drawn in a space, in 3-dimensional space. Okay, and then when you have these lines coming through, let's say this piece of paper, right? The density of these lines going through this piece of paper actually is proportional to the magnitude of the electric field itself. Okay, and this is actually quite an important concept. So what field line determines is the density of these lines. So what you can then tell is if I draw a line here, let's look at if I draw a little surface here. So let's imagine we have these 2 positive charges close together in space. Then, okay, of course, here I've drawn the lines in 2-dimensional plane, but you can imagine that these lines should be in 3-dimensional space. Okay, then I can put a little piece of paper here of the same size. And as I am closer to the positive charge, the density of the line going through that piece of paper is going to be much larger than when I'm further out. Because when I'm further out, remember the lines can only start from the positive charge itself. So when I'm further out, there is less and less number of lines that will go through the fixed size area of my paper, right, in the space. So that means as I'm moving further away from the charge, my electric field is decreasing, which actually agrees with the equation where we had the electric field equation was the Coulomb's constant Ke times Q divided by R squared, right? So as we go, R is the distance from the charge to the point in space. So as we move further away, then the number of lines passing through my piece of paper, which is fixed size area, is going to decrease at a rate of R squared, decrease at a rate or inversely proportional to R squared. Okay, so that's what it means by this rule number 4, density of the field line passing through a surface represents the magnitude of the field. Okay. So I would like to give a summary, and then I'll come back to that question. So we've been talking about electric force, which is the Coulomb's force. So when you have 2 charges, two charged particles, let's call it charged particles, then there will be a force acting on each other depending on, and then the direction of the force will depend on in which whether the two charges have the same sign or the opposite sign. And then we talked about electric field. So electric field is how the force will act if you had a test charge. So what is the general direction of the force when you had a small positive test charge caused by this big charge here? Okay, so that's the definition of electric field. And in order to calculate an electric field at certain point, you need to do a vector sum, okay, caused by each of these point charges at that point. And likewise, with a continuous charge, instead of having a point charge, now you have to divide your continuous charge distribution into small elements, and then you add all the components together into you add all the little components of the electric field caused by these little charge elements, and then when you do the vector sum, you will eventually get the total net electric field acting on that point there. Okay, and then we've discussed about electric field lines, which you can see an example here. So the field lines, they will start from positive charge, they will end at negative charge, they will never cross each other, and then the density of the electric field line is proportional to the electric field, the magnitude of the electric field at that point. Okay, so I will end the lecture, but I will take the questions. Okay, so thank you very much, and I hope to see you next Tuesday, which will be on Gauss law. Okay, so coming back to Matt, your question. Okay, so in this one, regarding half rod, must DL be a small point of the whole rod? Yes, so so we try to calculate the contribution from each of these little elements there, because instead of having some point charges, we have a charge that is distributed over the entire road, right? So we cannot actually consider this to be a single point charge anymore, because it occupies a certain space or a certain certain length in space, right? So that's why we need to compute. We need to consider these little elements DL, which is infinitesimally small. Of course, I can't draw infinitesimally small on this slide, so I have drawn relatively big. But we have to divide this into this little small elements, and then we need to compute the DE of each of these elements. Okay, we need to compute the DE of this element, and then that gives us if you add all of these contributions together, then that will give us eventually the net electric field acting on that point there. So that's why we need to rely on this integration, because what this integration means is we start from 0. Theta is 0. So when theta is this angle here, right? Theta is the angle from this line until where we are at the DL. Okay. Of course, there is this little element called d theta, but because d theta is so small, the theta is always going to be just somewhere, you know, the d theta is so small that we don't really need to care about that. But when you put the theta here and you start from 0, means you start calculating the contribution coming from this little element there, and then you move next. You do the integration up until you reach pi. Pi is what? Pi is 180 degrees, right? So these are all in radians, just for your information. So we reach 180 degrees or pi radian, and then at that point we have computed all the contribution from all of these little elements along the arc of the semicircle. Okay. So that is why we need to use DL, right? That is why we need to use. Now your next question is, can you elaborate on R times theta? Okay. Where is R times theta? Z. Are you talking about R times d theta? Or Yes. Okay. So R times, so we try to get this dl, the actual physical value of that dl. How do you do that? Then dl is just that arc length formed by the angle d theta, right? So if theta is, or if d theta is represented in, expressed in radian, then the arc length is always given by the radius times the angle. Because let's say, what is what is 360 degrees in radian? 360 degrees in radian is 2 pi radian, right? 2 pi radian. So 360 degrees is the entire circle. So if you multiply 2 pi and then radius r, you get 2 pi r, which is what? Which is actually the circumference of a circle. And you get the circumference of a circle because 2 pi radian or 360 degrees is a whole circle. Now you want to get the arc length. Arc length is then given by the angle which that arc length is drawn with times the radius, and that angle must be represented expressed in radian, of course. So 1 radian by definition, what it means by 1 radian is the angle that makes arc length that is same as the radius. So 1 radian, the angle of 1 radian by definition means that angle which makes that arc length to be same as the radius. Okay, if you use that definition, then you know that by multiplying r and the small angle d theta, you will get that small length dl, the arc length dl. Does that clarify your question? So to give you another picture, do I have that? Yeah. So I have this whiteboard. Maybe I can use. Okay. When this radius r, and then this arc length is r, that angle is going to be 1 radian. Okay. That's why when you have semicircle, this angle is 180 degrees, right? 180 degrees, which is equal to 1 pi radian. Okay. And if this is r, how do you calculate this is r? Bad writing. How do you calculate the arc length? How do you calculate the arc length? It's going to be half of the circumference of this circle, right? If I had a circle, it will be half of that. And you know, 2 pi r is the circumference of a circle, so it will be 1 pi r, and you can see that it is exactly 1 pi radian. So 180 degrees is going to give us the arc length of pi r because it's 1 pi radian. Any other questions from? If you still have doubts, you can ask me, please. So if you have questions, please do unmute and speak or type in the chat box. I'll probably stop the recording.